You're watching QRP to QRO. This is video number 3, replacing the ceramic receive filters in the second IF stage in a Yaesu FT-857D. The supplier of the ceramic filters used in the FT-857D, among other radios including the FT-857D, FT-2000D, as well as other non-Yaesu radios, including some Kenwood TS-2000s, had a production run of the filters where the housings were not properly sealed. During the manufacturing of the radios, automated wave soldering is implemented to attach the components to the boards. After this process of wave soldering, the boards go through a cleaning flush to remove flux from the boards. This process should not normally cause problems for these types of electronic parts. However, because of the poor sealing on the filter cases, the fluid used in the cleaning flush was able to enter the filters where it normally would not get in. We'll take a closer look at the block diagrams and schematics later to illustrate the theory of operation farther. One fact of the design of the circuitry in which these filters are placed is that DC voltage is present across the filter plates. These filters aren't normally to have DC voltage present across their plates. However, the filters are passive, and DC voltage being present should not cause concerns. Because of the design having such DC voltage present, the combination of the voltage with the fluid in the bad filters over time causes the fluid to crystallize. It also allows electromigration to occur between the plates. Electromigration is a process of material transferring through the conduction of electrons. Over time, this transfer of material shorts out the filter plates. That ultimately is what kills the receiver in the affected radios. The 3 filters that had this problem in my radio, serial number 8G910751, are pictured here in the red box. You can visually see the crystallization on the outside of the filter housings. They look like glazed donuts. The technical document that I'm referencing in this video is the Yaesu Technical Supplement, otherwise known as a service manual, for the FT-857. The part number of this particular one is EH007M90A. If you do a search on the internet, it should be easy to find. An important note here is that there are changes over time in these radios. As those changes occur, so too do the technical supplements or service manuals, so they correspond to the changes. There may be a lot of carryover between versions. However, you want to be careful that what you're attempting to work on is described in the particular manual that you choose as a reference. Case in point, later I will describe a modification to protect the filters after repair. Yaesu added this protection in later models of the FT-857D from the factory, so the problem this video is addressing should not exist, and the modification would be completely unwarranted, as the board is already set up from the factory that way. I do not have any specifics on serial number breaks of the changes. If you research online, you should be able to find that information. As to the filter problem, as I have shown, it is immediately visually evident with a quick look inside the case. Later in the video, I have a sample of the FM receive audio with the bad filters so you can hear the problem as well. I won't go over everything here in the technical supplement or service manual. If you are curious how anything in particular works, I recommend that you obtain a copy of the technical supplement yourself. You will likely want to start with the circuit description for theory of operation. Then from that, work into the block diagram, then to the schematic. I'm going to save quite a bit of time here in the troubleshooting, as we already know the filters are suspect. I will zoom in on the bad filters so we can take a closer look at them. They are labeled CF2, CF3, and CF5. These will correspond to CF1002, CF1003, and CF1005 in the technical supplement. We're going to start on page 8 in the technical supplement, the circuit description. For the focus of this video, I'm going to cover just the portions that are pertinent to the problematic filters specifically, with only a broad overview of the signal path through the receive chains, as that will help you understand the function of the filters and where they are placed. We know the filters are in the second IF stage already, so we'll find that here in the circuit description. We find that on the bottom left. Down here we find the second mixer circuit / second IF circuit. So we'll go ahead and read through here. The second mixer consists of FETs Q1083 and Q1084 on the main unit, where the first IF signal is mixed with the second local signal, 67.875 MHz. The resulting output signal, 455 kHz, is applied to the second IF filter, which is matched to the receiving mode, either CF1004, CF1005, or an optional mechanical filter. Now if you notice in that description there is an additional filter mentioned, CF1004. This happens to be the large silver blue labeled Murata filter that lies underneath the three filters in question. Although it is somewhat part of the same circuitry, it's a completely different style filter that's not prone to the issue. I'll come back to this filter again when we talk about the schematic, as there is a reason to point it out in relation to CF1005. So if we go back to the description, what's important to note here is the resulting output signal, 455 kHz. That's the frequency of the second IF. And we know that the filters are part of the second IF, so that's the part of the chain that we need to concentrate on. So we found CF1005. We still have two other filters to locate. If we keep reading down through the circuit description, we'll get down to the FM IF circuit / FM demodulator circuit. So we'll go ahead and read through here. On FM, the second IF signal passes through the buffer amplifier Q1094 and second IF filters CF1002 and CF1003 to the FM IF IC Q1080, which contains a mixer, limiter amplifier, filter amplifier, squelch trigger, and demodulator. So here in this description we find our CF1002 and CF1003. We'll move on to the block diagram on page 8 in the technical supplement. To start off, we'll zoom into the upper left where we will find the antenna connections. First of note in the block diagram is the dashed lines between the blocks represent transmit signal paths, whereas the solid lines between blocks represent receive signal paths. Shown here are the receive paths traced for ease of reference. I won't get into the details of everything in the diagram, however I want to point out the receive signal flow overview so you can better understand the function of the filters. We'll follow the receive signal path down to the next section of the receive chain, where we find our individual band section filtering. On the top of this section we will find the HF through 6 meter portion traced with red. Next down we find the aircraft band traced with blue, and below that we see the 2 meter band traced with yellow, and on the bottom we find the 70 centimeter band traced with brown. If you notice, below the 70 centimeter band you will find the wideband FM broadcast portion. I traced that in orange here. I won't spend much time on it as the signal does not pass through the problematic filters. It is demodulated right here in a dedicated portion of the receive chain, then passed on through a signal switch, again diode switching, to a buffer amplifier, among other sections, to isolate and filter the audio. Going back to the receiver chain we are concerned with, we'll follow the signal from the bandpass filter section to the first mixer. Here we find our first IF frequency, 68.33 MHz. Continuing on, we find our second mixer. From the bottom enters our second local signal, 67.875 MHz, and the operating frequency of the second IF, 455 kHz. I won't trace all the signal paths through the individual filters. These filters pertain to the different modes as noted in their filter sections if you look at them closely. The top filter is for AM. This happens to be CF1005. This is one of the three problematic filters. Looking on the top, I have traced the FM signal in red as it goes to a bit different section of the block diagram. Following that FM signal down, we get to the FM mode filtering. Here we find our other two problematic filters, CF1002 and CF1003. I'll pause here for a moment. What is also important to note is that up until this point, all of the signal tracing that has been done has been in the RF domain. This is where the mixers perform their work and where the IFs, or intermediate frequencies, come into play. The RF is combined through a mixer to a common frequency range. This way the receiver can work within a narrow range of frequencies. The questionable filters lie in that last RF level IF signal at 455 kHz. Depending on the mode selected, the bandwidth of the filter that the IF passes through changes. Each filter has a different bandwidth to, generally, accommodate the mode of operation. We will take a closer look at the FM filters in the schematic. Though they appear together here in the block diagram, they are only loosely related. The schematic will show us the difference. At this point in the receive chain, we followed the RF signals to their endpoints. Each one of the signal paths will end up through switching corresponding to their type of modulation in a detector. This is the demodulation point. What comes out of the detector is demodulated audio. Highlighted here in the red box is the FM detector, for example. Next, we'll move on to the schematic diagram on page 23 of the technical supplement to look at the circuitry of the filters in more fine detail. Again, I won't go into everything in here, only the bits pertinent to the filter functions and the signal paths through them. The first filter that we'll take a look at is CF1005 in the AM chain. Going back to my earlier description in the opening of this video about the voltage being present on the filter plates and that causing corrosion or crystallization of the fluid, as well as electromigration, I've added the red trace here to show the signal voltage to illustrate that. I won't go into much detail here about where the signal comes from or how that works exactly with diodes to create the switching effect. However, the basic principle here is that voltage is sent to the circuit from a microcontroller, or IC, to activate a diode to conduct. This conduction between diodes is what pulls and directs the signal through the received stages, just as we see here with CF1005. Since the filters are passive, they in and of themselves block the DC switching voltages, in theory. When the corrosion and electromigration happen, that allows subtle arcing to occur between the plates. This causes a popping noise in the receiver. Due to the corrosion and improper filter operation, the signal levels will appear lower and have a grainy or sandy sound. Following shortly, you will see an example of the receive audio in FM with the bad filters so you can hear exactly what the audio sounds like. I don't have any examples of other modes, unfortunately. Next, we'll look at filters CF1002 and CF1003 in the FM chain. Again, I have highlighted the paths of the switching voltages for reference. Additionally, I have separated the signal paths, highlighting the diodes used for directing, with yellow corresponding to FMN, or narrow mode FM. The FMN that is circled is in reference on the schematic to the switching voltage source. Not pictured in the screenshot is the regular FM switching signal source. I have added the FM-W note for clarity to differentiate that from the FM-N that you do see in the frame. Therefore, CF1002 corresponds to narrow FM, and CF1003 corresponds to normal or wide FM. As mentioned in the beginning of the talk on the block diagram, wideband FM, the broadcast band, has its own section of the receiver and is demodulated there. There is no signal from this section of the receiver that passes through CF1003, even though I have it marked as being for wide FM. They are two totally different sections. Following is an example of the receive audio on FM with the bad filters. Note the graininess of the audio and listen for the popping noises I mentioned earlier from the subtle arcing in the filters. It should be very distinctive.
So I had a long incubation period for about 4 or 5 days. I got it 2 weeks ago Friday, and I started Saturday, and I started feeling a whole lot better. But
I think it goes pretty well without needing to be said that the fix for this issue is to replace the filters. If you research this issue and find others that have done the repair, it's commonly described as being a major pain in the ass. I wholeheartedly agree with that statement. The biggest challenge in the removal of the filters is that Yaesu used high-temp, lead-free solder. Even with an 800-degree tep iron or desoldering iron, the lead-free solder is very difficult to work with. It also does not mix well with 6337 or 6040. I tried using both types of solder with solder wick and flux to attempt to get the lead-free solder to flow out of the through holes. It was a fruitless effort. Thanks to a friend of mine, Jason N8XE, we tag-teamed the removal of the filters. They came out in pieces. The overall object of the game we came up with was I would apply heat on the back side of the board and Jason would use a pick to pry underneath the filters. Essentially what we did is we broke the filters apart and pulled them off the board one pin at a time. A little heat, a tweak of the pick to pull the filter up a bit, and then on to the next pin. This was not a fun process. The most important point to keep in mind is to avoid board damage as much as humanly possible. This is extremely difficult to avoid in this environment. Along with board damage is the point about plated through holes. It's imperative to not pull a through hole. Once the filters were removed, I used a micro drill bit to open up the rest of the solder down inside the hole. This is really a very poor option, however we did not have enough heat to get the solder to flow any way we tried. Cutting the solder, at the risk of damaging the through holes, with the drill bit was the last resort to open up the holes, but it worked. During the solder removal attempts with solder wick, I managed to pull off a surface mount resistor. With as small as it was, I taped it to a piece of paper, so when I got to installing the new filters, it would be easy to find and put back on. The installation of the new filters was very simple. Reattaching the surface mount resistor was a bit tricky. Again, with the very small size of it, about half the size of a grain of rice, it required a lot of finesse and care to get back in place on its solder pads. Thinking back to the beginning intro to the problem that is the subject of this video, one common modification at the time of the filter replacement is to isolate the filters from the DC voltage. We'll take a look at CF1005 here to discuss the point. I'll also bring in CF1004, seen below, into the discussion in a minute as well. As I mentioned in the beginning of this video, the presence of the DC voltage should not cause concerns if the filters were not contaminated by the cleaning solution. This is because the plates of the filters act as almost a capacitor already. The plates are insulated from each other, not directly connected. Capacitors pass AC and block DC. In the case of the filters pass the RF signals through them as switched and directed by the signal voltages as described earlier. The AC RF signals, therefore, are allowed through the filters and DC blocking capacitors, whereas the signal switching DC voltage is not. If it is desired to isolate the filters, it would be appropriate to install 0.01 microfarad capacitors on the signal traces leading into and out of each filter. I have illustrated the placement of such blocking capacitors here in reference to CF1005, noted by the blue marks. I'm not going to go into detail on the actual board placement of the blocking capacitors here in this video. However, between the schematic and board layout diagrams in the technical supplement, it should be very easy to locate where to place the capacitors with respect to CF1002, CF1003, and CF1005. Hint, they are placed on the bottom of the board, and it may be required to relocate some of the surface mount resistors or replace the surface mount resistors with axial to reach across traces between other existing pads. It is not a very difficult job so long as you can source the parts. At the time of the repair, mid-December 2019, and creation of this video, February 24th, 2020, I have not sourced capacitors for the blocking modification. At the time I ordered the filters, Yaesu did not have any suitable capacitors in stock. As the modification is not critical to normal operation of the radio, I'm not concerned about them at this time. While we're on the subject of blocking capacitors, let's take a look at CF1004 now. Let's go ahead and trace where the signal voltage is present on this filter. If you notice, the circuitry is identical to CF1005, with the exception that, as is highlighted in blue, DC blocking capacitors are present on the board to protect this filter. One quick note about later FT-857Ds as well. Yaesu did add DC blocking capacitors to the boards, 6 in total, 2 per filter to block the input and the output from DC. For an example of the board with the blocking capacitors added from Yaesu, look up the blog by SV8YM, that's Sierra Victor 8 Yankee Mike. He has documented that and has provided a serial number for reference. Since the receive audio example I provided earlier to audibly describe the issue was FM, following is a recording of the radio receiving FM clearly with the replaced filters to make the point of the successful repair.
Rain 30%. Here is the nearshore marine forecast for water. On the latest weather map, a cold front will move southeast across the region through early Tuesday morning. Low pressure will move northeast through the area by Wednesday. 80%. Wednesday night, cloudy. Rain likely with a chance of snow in the evening. Cooler with lows in the upper twin T's. West winds 10 to 15.
Also of note is the very beginning of this video showed activity on the 40 meter band on lower sideband, with the S meter responding accordingly. Not shown, as unfortunately I don't have any recordings of it, is that the receiver gain was also stuck upon the replacement of the filters. I went through the receiver gain alignment with my service monitor and was able to get the receiver gain to function properly. Now the S meter is properly calibrated with proper response all through its range. The receiver gain alignment of the FT-857D may be the subject of a future video. Stay tuned. That concludes this episode of QRP to QRO, video number 3, replacing the ceramic receive filters in the second IF stage in a Yaesu FT-857D. If you like what you saw in this video, found it informative, or found it very helpful in your own amateur radio endeavors, please leave a comment and click on the subscribe button under the bottom right of the video, and as I post new videos you'll receive email notifications. Thanks for watching in 7.3. I'm Steve, KC8QVO.